When two independent servers generate identical identifiers, the resulting collision overwrites critical data records. The failure is silent, and it destroys data integrity. Generating a single unique ID on a single machine is trivial. Scaling that process across millions of decoupled events running on dozens of distinct servers without duplicates is an architectural nightmare. Traditional database features like the auto-increment primary key break down in a distributed environment. They assume a single source of truth is keeping track of the current count. Under high load, routing every ID request through a single database server creates an immediate throughput bottleneck and a fatal single point of failure. Achieving distributed scale requires abandoning centralized counting in favor of decentralized generation. Any viable distributed ID architecture must satisfy 5 rigid constraints. The IDs must be numeric. Alphanumeric strings index poorly and heavily degrade relational database performance over time. They must fit into a 64-bit integer. This enforces maximum storage efficiency in memory-constrained environments. They need to be roughly time-ordered. Chronological sorting allows the database to retrieve sequential records naturally without running expensive reindexing operations. The system requires a throughput floor capable of generating over 10,000 unique IDs per second to keep up with high concurrency traffic. Meeting all 5 of these technical requirements simultaneously is the primary challenge of distributed ID design. This diagram shows multi-master replication. It uses a stepping approach where database servers increment IDs by a fixed value. Here, one handles odd numbers, another evens. This distributes write load, but the logic is brittle. The stepping math collapses the moment you add a new database server to handle increased traffic or remove an existing one for maintenance. Operating this across multiple geographically distant data centers requires perfect network coordination, introducing severe latency. Because different servers experience different load profiles, the IDs generated across the cluster do not strictly correlate with time. Multi-master replication works for static infrastructures, but it lacks the flexibility required for elastic systems. Universally Unique Identifiers, or UUIDs, offer a completely decentralized option requiring zero coordination between servers. But UUIDs fail our hardware constraints immediately. They are 128 bits long, which doubles the required storage space per record compared to our 64-bit limit. Their absolute randomness destroys index locality. Writing completely randomized strings to a database causes severe storage fragmentation and degrades write speeds. Because standard UUIDs contain no chronological data, any time-based queries become significantly more expensive to execute. Implementing UUIDs trades immediate generation ease for long-term database degradation. This schematic illustrates the ticket server model. Every web server in the cluster requests its next identifier from one central database, dedicated entirely to counting. It outputs clean, purely numeric IDs. For small to medium-scale applications, this architecture operates reliably. However, if that central ticket server goes offline, every dependent system halts immediately. Data creation stops. Setting up multiple ticket servers to avoid this failure point reintroduces the exact data synchronization problems we tried to eliminate. Under massive request volume, the network latency required simply to reach the ticket server becomes the absolute throttle on the entire system's throughput. Any architecture requiring permission from a central authority is unscalable at this magnitude. This chart details the Twitter Snowflake bit layout. Instead of a single counter, it divides a 64-bit integer into distinct sections. The first 41 bits represent a millisecond timestamp since a custom epoch. This enforces chronological sorting, providing 69 years of capacity before integer overflow. Next, 5 bits dictate the data center ID, and another 5 bits dictate the machine ID. This pins the identifier to its exact physical origin. The final 12 bits hold a sequence number. If a single machine generates multiple IDs within the exact same millisecond, this sequence increments, allowing up to 4,096 unique IDs per millisecond on each machine. The web server pieces these bits together locally. It never queries the network to get its next ID. This flowchart demonstrates how the resulting binary string converts into a decimal format, yielding a UTC timestamp for auditing purposes. Because the generation process is entirely local to the server, network latency drops to 0, and the centralized bottlenecks are eliminated. By encoding this environmental state directly into the ID, Snowflake produces a compact 64-bit fingerprint of a specific moment in space and time. This system requires flawless infrastructure management. If you accidentally deploy two machines with the same data center and machine IDs, they will immediately generate overlapping integers. But Snowflake's most critical vulnerability is its absolute reliance on time moving forward. Network time protocol rollbacks force the server's time backward. When this happens, the generator could output duplicates for a millisecond it believes is new. Engineering teams must implement defensive logic, either pausing generation until the clock catches back up to the furthest point reached, or failing requests to protect the database. High-availability ID generation requires mathematical encoding backed by rigorous real-time clock monitoring. We now have hundreds of decoupled nodes churning out fully sortable 64-bit unique IDs at millions of operations per second. The solution to distributed scale is moving from global coordination to local encoding. With a collision-proof ID generator in place, we can tackle the next architectural challenge, building a global URL shortener where these IDs become the foundation of the entire product.